All right, we are live. So in this video, I want to talk about solving second order differential equations. And the same idea, the trick is going to arise when we do higher order differential equations. But the key thing to recognize is that ODE int is only set up to solve first order differential equations. By first order, I mean you only see things like dx dt. A second order would be dx squared dt squared. But as I'll show you, there's a simple trick that can convert higher order differential equations into coupled first order differential equations. And so let's just motivate this example. So imagine we're trying to solve this differential equation right here. Y double prime, so what I mean by here, I'm just doing simpler than this is dy squared dt squared plus 0.4 dy dt plus y is equal to some arbitrary function f of y comma t. So this is a second order equation because we have a double derivative on the y term. Since it's also a second order differential equation, we also will require two initial conditions, one for y and another for y prime or dy dt at t equals 0. So these are our two initial conditions for the second order differential equation. So the trick in this to convert this equation up here into a first order equation or two coupled first order equations, so we're going to define two dummy variables. So the first dummy variable, x of 1, that we're going to just set equal to y. And then we're going to set x of 2 equal to y prime. So these are going to be our two new variables, one set equal to y and one set equal to y prime. And now we're just going to take the derivative of these two dummy variables. So if we take the derivative of x1 with respect to t, so x1 is equal to y, so its derivative is going to be simply equal to y prime, but we know y prime is equal to x2. So we're going to get x1 prime is equal to x2, and that's going to be our first differential equation. And then we're going to take x2, and we're going to take its derivative with respect to time. And since x2 is equal to y prime, then x2 prime will be equal to y double prime. And now once we have y double prime, well, here's y double prime. Well, that's just simply equal to f minus this term and this term. So that's f of y comma t minus 0.4 y prime minus y. So I'm just putting the y prime on the left side of the equality and everything else to the right side of the equality. Now the last thing is just to replace the variables y with their associated x values. So when we replace the y, that gets replaced with x1, right? So that's just the definition of x1 is equal to y. And then we have minus 0.4 times y prime. Well, y prime is simply equal to x2. So we're going to have 0.4 x2. And then we're going to have minus y. In this case, it's just going to be simply the y, which is x1. And if you look at this, we have two differential equations. I can write them just here, right? We have x dot of 1 is equal to x of 2. And then second is we have x dot of 2 is equal to f of x1 of t minus 0.4 times x of 2 minus x of 1. And so these are our two differential equations that are equivalent to this second order differential equation up here. Same trick can be applied to third and fourth order differential equations, in which case you can take a fourth order differential equation and represent it as four coupled first order differential equations. Though at least in chemical engineering, it's rare to see differential equations with terms higher than 2. And so I'll just stop there. And so if I want to solve this equation, so let's maybe, let's pick a value of f. Let's just make x of f of t is maybe, let's just do exponential of minus t. And maybe we'll set, let me come over here, y of 0 is equal to 1, and then y prime of 0 is equal to 0. These two equations, of course, will tell us that, just by looking at the definitions up here, that x1 of 0 will be equal to 1, that x1 of 0 will be equal to 1, and x2 of 0 will be equal to 0. So that's kind of what we're recasting here. So we can define our f. Let me call this g and z comma t. And we're going to have x1 and x2 is equal to z. So we're going to unpack it. So this is going to be the differential equation with all this junk over here. And then we can just simply return. So equation 1, or we can say x dot of 1 is, so x dot of 1 is simply going to be equal to x of 2. And x dot of 2 is going to be this function, right? And this function, we're just going to simply, I should put x1 there. It's going to be simply the exponential of minus t. So it's going to be a decaying term. And then I'm going to have 0.4 times x of 2. And then I'm going to have my x1 term. And then I'm just going to return x dot of 1 and x dot of 2. And so my initial condition, z naught, in this case, is going to be 1 comma 0. And then let's look at a t-span of NP Lin space of 0 comma 20 1,000. And so then we can just solve this equation. Z is equal to OD int of G, Z naught and T. And I have an error, NP Lin space, and X is not defined. Let's come back up here. And that's not X, that's my Z term. So now it runs. And then my Y, which is typically what I want, is going to be 0 tilde comma 0, because it's going to be the first solution, right? So remember, Z is going to have the two variables as columns. So x1 will be the first column, x2 will be the second column, where this is y and y prime. And so I come down here and I grab that first column, and then I can just do PLT plot of t comma y, line width is equal to 3, color is equal to red, and then PLT show. Typically, when you solve second order differential equations, you don't really care about plotting y prime. You only really consider about plotting the y solution. But if we wanted y prime, y prime would be equal to z tilde comma 1. And so I run it, and that would be y. And if I wanted to look at y prime, right, I could run this solution, and it's going to be basically the time derivative of the other solution. So again, typically you only want to look at y, but that's kind of the general structure for solving a second order equation. So if I come back up here, again, the key thing is just defining these variables, x1 and x2. And by defining x1 and x2, I can recast this equation in terms of this equation and this equation over here. So basically, once again, the second order equation becomes two coupled first order differential equations. So with that, I'll stop. This is pretty short. It's a pretty simple trick. Once you understand it, then it's basically the same as solving, first order differential equations, but it's a useful trick. And because this trick exists, none of the people that develop integrators for ordinary differential equations bother to specialize their integrators to second or third order differential equations. Basically, they always focus on the generic form of x dot equal f of x comma t, because that's kind of the general structure that these integrators try to solve. So once again, if you have questions, please post them in the comment section or on Piazza, or send me an email. All right, thank you. Cancel.